Hi guys. So in this video, we are gonna discuss about LDE, limited direct execution method of early days, which tells us how older CPUs used to execute any program on a CPU. How the operating system handles everything when we run a program. So this LDE stands for limited direct execution. And the term direct execution simply means we take our program's code and directly send it over CPU and CPU runs it. That's it. Okay, so if we see here, suppose that we clicked a program that is available in some of our directories. So what operating system does, it creates the entry for that. It creates a new entry in our process list, allocates some memory for it in program, then it gonna load the program's code into memory and set up the stack with command line arguments. And then in our program, we might have some starting of functions like in C++ or C, we have something like main. So start executing main, and then it does program does all its work, and then it return from main, and the OS frees up the memory that it had already given to the program. So this is what is direct execution. Take a program, run on CPU directly, and once it's done, release the memory. But what about this thing? Limited. So see, there are some problem with the direct execution method. Suppose that a program is there and you have given the complete CPU to that program. What if that program tries to do some restricted operations, like the program is trying to read your um, some disk input outputs or hardware or network, something that it shouldn't do, or it should something that the program is not allowed to do, it can do that thing. So how OS operating system gonna implement restrictions to the a program that is running on your CPU? The next thing, we also know that our CPU has maybe 8 cores, 4 cores, 2 cores, something like that. So how we are able to run multiple process on a 2 core or 8 core CPU? So we do that by switching the process in between again and again. So that is also a question. So how does OS switch process? How does it know that, oh, it's time to switch? And this switching thing is time sharing, and why there is time in the name, I will explain you in a little bit. So let's first study about the first problem. So the first problem was about restricted operations. We don't want a program to do something it is not allowed to do. And to implement this thing, the early developers of operating systems come up with a solution known as mode of execution, or simple modes. So this mode defines the mode of execution, in which mode your program will be running. So there are two modes in which a program can run. One is user mode and another one is kernel mode. So by the name, uh, you can easily understand the user mode is something that runs in a user space. And by user space, I mean it is a space where you can't do any privileged task. You can't delete some root files and which are owned by root user. You can't do that. But in kernel mode, this runs in kernel space. Here you have the maximum privilege and maximum power. That means you can do anything here. Okay, so how we handle the restricted operations? We introduced modes of execution. Modes of execution means the program gonna run in which mode, user mode or kernel mode. User mode runs in user space where you can't do privileged tasks, but the kernel mode runs in kernel space where you can do privileged tasks. Simple. No, it's not that simple, because still there is one question. Suppose I double click the program it started running in user mode, how does this program will go to kernel mode? If any program can go to kernel and do privileged tasks, it would be so easy to take access of our private files, our root files, but it's not. Because with the design of mode of execution, the developers introduce what we call system calls. System calls take a program from user space to kernel space to do some privileged task. To do some tasks they are not earlier allowed to do. Now let's study about system calls. How system calls works. Suppose here is a program, double clicked it, the program started running in user space. And now this program wants to do some privileged tasks, maybe want to read some file that it is not allowed to read, like your input files it want to read. So what this program does in user space, it executes a trap instruction. When the trap instruction is executed, your program shifts to kernel space. And once we shift to kernel space, we do all the privileged tasks, we read all the files that we want to read. And once we are done with everything, the operating systems again execute a return from trap instruction, where we again go to our user space. Another important thing that I want you guys to note here, that program executes trap instruction and OS executes return from trap. That means OS decided when to return from trap and program decide when to go inside a trap instruction or kernel mode. So in a layman language, we can say that system calls are nothing. They are combination of trap instruction plus return from trap instruction. Whenever we do a system call, we are executing a trap instruction to go from user to kernel space. We do all our previous tasks there, and then we come back to the user space by executing return from trap instruction. And this is done by program, and this is done by operating system. Now there might be one doubt to you guys, that when we jump from user space to kernel space, and after doing our work, when we come back to user space again, how does we know where were we last time? So there is a important thing in Linux kernel is kernel stack. It is a per process. That means each process is going to have its own kernel stack, which we will use to store the current state of program whenever we jump from user space to kernel space. And by current state means the program counter, like where are up to where we have executed our program, and other necessary registers, like if you want to store some data and something like that. Everything is stored in kernel stack, and kernel stack is per process kernel stack. That means each process is going to have its own kernel stack. And when we are going to use it, whenever we move from user space to what, kernel space. Another important thing, we studied about system call. They are nothing, they are just trap plus return from trap instruction combination. But whenever a program runs trap instruction, it doesn't specify a memory that you have to go to this memory and you will find a code that you will execute to handle this trap instruction. If it can do so, it can easily manipulate that memory address and whatever instruction written to handle that trap also. So to prevent that, whenever kernel boots up, it sets up a trap table where it maintains a table. We have like trap name or trap instruction. Here we have trap name and name, what the trap is called, what code it should execute, and where that code is present. Something like that. It's a very, I'm explaining you guys in a very layman language, but the logic is correct. So the kernel sets up trap table at boot time with instructions and where are those instructions available in memory, so that hardware can execute whenever the trap instruction executed by our program. Okay. Also, each system call has its own system call number. It's a very basic thing. Yes, every system call has its own system call number. So why we do these things? Because we want the control to stay to OS, not to program. And how trap table ensures that? Suppose a program wants to execute an instruction, a trap instruction. So now it is the job of operating system to find that code that it needs to execute for that particular trap instruction. The program don't have the power which instruction it contain. It can only call an instruction, but the under beneath the logic of that instruction can only be executed by operating system, and only the operating system knows where the trap table is. It finds the trap table, finds the set of logic and instruction for that particular trap, tells the hardware that you have to do these many instructions now. Once the CPU does all those things, again execute return from trap and go back to the program in user space. So this is something. This is a picture from uh, Operating System 3 Easy Pieces book, which is a very good book. You should read it. If you don't want to read it, you can subscribe to me. So this is the all the flow of our program or our operating system. So when OS boots at the first time, it initializes a trap table. So it remember address of syscall handlers. So whenever we have some trap instruction or any system call, it remembered the address. Hardware remembers the address of those instruction, because hardware have to execute those lines of code whenever a particular instruction received by our hardware or operating system. Now this is the boot time thing where we set up a trap table. Okay, now when we click a application or something to execute, first our operating system creates a process entry in the process list, allocate memory to the program, and it also load the program into memory, set up stack and everything. Okay, then our okay, so this is our hardware kind side of thing. So we set up everything. We have stacked with our argument counts and everything, program counter and everything. Now we execute return from trap, and we go from kernel mode to user mode, where we execute our main function. Okay, and suppose while executing our main function, we come up with a system call, and whenever there is a system call, we're going to trap into operating system. So there might be a current state of this program, how much it is executed, what are the program counters, and what are the values stored in register, and it's going to have a lot of information at this moment. So what the hardware does, it save those registers or those information, it's per process kernel stack, and then move to the operating system to handle the trap handler. So it checks the trap handle table and execute those instructions from the trap table. Basically, it handles the trap here. Once the trap is handled, we go return from trap. Then again, these saved registers are restored from kernel stack, and our program counter jumps to here. Our We jump from kernel mode to again user mode, and here we see that we have completed our previous task. We do rest of the program and then we exit, and then operating system frees up our memory and whatever it allocated to us. So this is how the OS does all the things of trap handle, trap instruction, written from trap instruction, trap table, and everything per process kernel stack. Now let's come to the second problem, that is how operating system switch between process. Because if you see, if you think, if we don't do this thing, switching thing, what will happen? I write a program with an infinite for loop and I executed it. Now CPU will have that program for infinite time. It's never going to exit. So that's not a good thing. And also there is one more thing. Whenever we execute a program on our CPU, once it started executing, operating system lost the control. Now operating system can't stop that thing. But in modern CPUs and modern operating system can do that. We can open our HTOP, BTOP, and anything, and we can kill any process. How's that possible? Okay, so how OS regain control of the CPU? Because once we started executing a program, CPU lost its control over the CPU. Now that process is running on that CPU. So how OS gonna regain the control of CPU? Because if it is only possible for operating system to switch between process if it has the power to do so. So there are two methods to do so. One is cooperative and another one is non-cooperative approach. And the name suggests what these approaches are. So in the cooperative approaches, which was used earlier, the process periodically give up the CPU. Means whenever we write a program, the developer take cares of other programs also, and it deliberately calls a system call to leave the CPU for other process for some time, and then the other process also does the same, and all the programs work cooperatively to leave the CPU after a certain period of time. And how does the process periodically give up the CPU? With a system call, and this system call is known as yield system call. Yield, that means it transfers the control to operating system so it can run other processes as well. But what if a process is not cooperative? Suppose I intentionally designed a program that is not cooperative for other process. Like I intentionally put a infinite loop. And that's the same problem with earlier operating systems. You might have faced sometimes your complete PC is hanged. You can't even move your mouse. The only option you had is to restart. That's the actual case of cooperative approach, where if a program refuses to give up the CPU, then there is only one thing you can do, that is restart, reboot the system. But that's not the case with non-cooperative approach, which is the advanced version. Here what we have a timer interrupt. So what this timer interrupt do, it raise the interrupt after a certain period of time, like X millisecond it is written in operating systems. Okay, so timer interrupt raise the interrupt after a particular time, and then it handle this interrupt. Because once we raise an interrupt, we gave the control to the operating system. Okay, so what we do in non-cooperative approach, we have a timer interrupt which raises an interrupt after a certain period of time, which is very small by the way. And then we jump to the interrupt handler and execute those lines of codes. Now there's also again one more thing, that when we jump from one process to another process, we have to store the state of this old process. So after some time, when we again jump back to the first process, we can continue from where we left off. Okay, so now let's discuss about complete thing, including complete flow of our operating system to solve both our problems. Okay, and this kernel stack is used to store the state of that what we say program before switching. So this is here operating system boots it in initialized trap table. Okay, now the hardware remembers all the address of all the traps and syscalls. Okay, then operating system also starts a interrupt timer which sends a interrupt CPU in certain after every certain period of time. Okay, these two things are used to handle our two problems. One is the trap for the first problem where we want to do restricted tasks, and another one is to solve our second problem where we want to switch between the processes. Once the uh, operating systems started, suppose that we have a process A. Suppose that we have process A that is running and certain time passed and timer interrupt kicks in. So whenever timer interrupts kicks in, the in this what we say interrupt handler is executed, and first thing it does, it saves the state of the process A, and to save the state, it saves the registers of A in kernel stack of A, which is a per process kernel stack, by the way, and then it moved to the kernel mode. Okay, and now we're gonna handle the trap where we can switch to a process, and this switch thing is decided by your scheduler, which we will discuss in next video, so stay tuned. Which is decided by your scheduler. That means whenever a process is interrupted by a timer interrupt, the operating system decides whether I need to continue this process A or I need to switch. Suppose that I was decided to switch, so it calls a switch routine, sorry, in which it saves the what registers of A in a place, okay, and restore the old process state in old process and store them in kernel stack of B, process B, and then return into here. Now we have kernel stack B contain all the state, which then restores into registers of B, and we move to user space. Now here we have the old state of our process P, and we continue executing this process. After some time, again an interrupt arises. We go to first hardware, save our state into kernel stack of P. Then we again go to operating system, where operating system decide whether I want to switch or not. If it wants to switch, it save this state, current process state in a place, and restore the old state, again come back to the hardware where it uses the kernel stack of other process, previous process, restore those registers and goes to user mode. So this is what is limited direct execution. That simply means we are executing our program directly on CPU, but with some restrictions, with some limits. And what are those limits? Those are two limits. First is limit of restricted operations, and second one is the process thing. And for the first problem, we are using traps, or we can say system calls, which are combinations of trap instruction plus return from trap instruction. And the other thing is switching of process, which is also done by a timer interrupt kind of thing, which execute a interrupt after every certain period of time, and then OS decides that whether it want to switch or not, and everything. Okay, so that's it. Next video will be on scheduler. If you want that video, please like, and you can share something in comments as well. What should I improve? What should I explain next? And everything. Thanks. Bye.